Well, hello everyone, and welcome to the 2021 virtual edition of the NSS Annual Convention. My name is Bill G. Today I'm going to be talking about a fairly interesting project called a Cave Intrusion Detector. So, giving a little bit of history on this before I get into the details of how this device works and how it's built. Some years ago, I became involved in Carroll Cave Conservancy. And Carroll Cave Conservancy owns, of course, Carroll Cave, which is the second or maybe the third longest cave in Missouri, a little over 20 miles. This cave was one of the feature caves at the 2015 NSS convention that was held in Waynesville, Missouri. One of my tasks in Carroll Cave and in the Carroll Cave Conservancy is to run a project to collect data regarding the stream level in the cave. We have sensors in the cave which collect about every 30 minutes a pressure reading from the depth of the water, and that can be converted into depth pretty easily and then graphed. The purpose of all of that is to get a correspondence between rain events on the surface and changes in the stream level in the cave. The project has been running for about 10 or 12 years and has been quite successful. You can see all of the data that we've collected over the years on the Carroll Cave website, https://carrollcave.org, and that's Carroll with 2 R's and 2 L's. So as part of that, I've been very interested in data collection in a cave. Some years later, probably 3 years ago, I saw an article in the NSS News regarding a cave water depth logger that was home built using an Arduino microcontroller. This is called the Cave Pearl Project, and there is a website for it, which I believe is cavepearlproject.org. I will verify that and put it in a subtitle or something in this video. The Cave Pearl Project took an Arduino microcontroller and wrapped it around a custom enclosure and a pressure sensor and turned it into a logger for checking water depth. The nice thing about it is the price. The loggers that we use in Carroll Cave are from HoboWare, from Onset Computing, and they cost about $500 each. They're rather expensive. They work extremely well. We've been very pleased with them, but they are very expensive. And so the prospect of using a data logger that could run for under $100 pretty easily was very interesting to me. So I bought some Arduino products and started investigating how I might build one of those. Shortly after that, one of the members of my grotto, Jim Cooley, came to me with a request. He had been asked by members of the Missouri Department of Conservation to come up with some method of finding out when and if humans are visiting a cave. The Missouri Department of Conservation owns around 1,000 caves in Missouri on their various properties, some of which host very sensitive populations of Indiana and gray bats. They don't have gates on most of those caves because gates are really expensive and it's a government business, so they don't have a whole lot of money. But they wanted to know if there was some way that they could put a logger in a cave that would detect if a human went in, log the event, and produce data for later analysis. Well, I thought this is just about like what we're looking at with Cave Pearls project and all of that. I looked around at some of the available parts for Arduinos, some of the sensors that could be had for it, and found that there are a number of light sensors. You can also get interfaces to put micro SD memory cards on it so you can record the data. And there are real-time clocks, which the Cave Pearl project had already been using. Real-time clocks so that you can figure out when something happened. So I bought more parts, assembled a prototype, and found out that, well, yeah, this is a good possibility. We went through several iterations of this device, and I came up with a version now that sits on a breadboard. And that is the version that I will be talking about when we get further into the presentation. Right now we have 2 of those out in caves for testing. One of them is in a cave called Slough Bottom Hollow, which is in south central Missouri, and the other one is in Carroll Cave. I will be getting data from both of those within a few months, probably not until after the convention is over with. So what I want to go through today in the slideshow that's going to be appended here is what are all the pieces and a large overview of how it all goes together. I have put together a group of videos which are on YouTube showing the details of assembly. There are also some documents including parts lists and information about the exact wiring and schematics and that sort of thing, which will be made available somehow. I'm not quite sure how I'm going to make those available, but somehow or another that information will be available to you. So without further ado, let's get into it. Before I get into many of the details on the Cave Intrusion Detector, I first want to acknowledge the input that came from the Cave Pearl project. I mentioned that in my videoed introduction, that the Cave Pearl project was one of the inspirations, one of the main inspirations for doing a cave intrusion detector. They have provided much of the technical know-how, especially around power saving techniques, how to get the Arduino into a low power mode and how to put it to sleep and how to really cut down on the power usage. Their original project was water depth data loggers using Arduinos, and that's how I came to first be interested in them. The Cave Intrusion Detector is mounted inside of a clear plastic container of some kind. In this case, it is shown with a 2-battery pack inside a 1-pound peanut butter jar. The 1-pound peanut butter jar is just about exactly the right size. It's not too big, it's not too small. It's a fairly easy container to hide in the cave. You can use a bigger container, that's not a problem, but it makes it a little bit more difficult to carry and to hide in the cave. The 1-pound peanut butter jar is certainly big enough for a 2-battery pack and probably big enough for a 4-battery pack, although you might have to get creative in how you get everything stuffed into the jar. The major components of the Cave Intrusion Detector are an Arduino Pro Mini microcontroller, a TSL 2591 light sensor, a DS3231 real-time clock, a micro SD memory card and the interface, a battery pack, and the total cost of these parts is around $40. About a third of that is the batteries. You can expect good 18650 batteries to cost you around $6 a piece. About another third of it is in the Arduino and the light sensor. The rest of the components are really cheap. The memory card interface, for example, is like 50 cents. Really cheap. I will go into, as I go through the components and talk about each one individually, I have a cost associated with it on the slide. This picture shows the prototype, the very first prototype that I built, which I did on a breadboard. This is the kind of breadboard where obviously you can just stick pins, wires with pins on the end into it and generate something up. This breadboard looks like a mess. It kind of is. I've had it wired and rewired several times. It was very useful to figure out just exactly how to wire the Cave Intrusion Detector. There is a memory card interface on this board. It's in the upper left corner, hiding behind the real-time clock. The real-time clock is standing on end instead of laying flat. On all of the other builds that I do, it lays flat, but there wasn't room on this one to do that, so I just leave it standing up. This one never goes in the cave anyway, so I don't have to make it as compact as the other ones. In the lower left is the light sensor, and in the right center is the Arduino microcontroller. You can also see the LED and the current limiting resistor in top center. The transistor, which controls power to the memory card interface, is not visible in this. This is a picture of one of the completed units, built on the latest standards and built on a breadboard. 3 of the components are visible here. You can see the light sensor is pretty obvious in the upper left. The real-time clock is in the center. The Arduino is on the right. You can also see the transistor, which controls the power to the memory card interface. You can also see 2 of the decoupling capacitors. There's one right next to the Arduino and there's one in the lower left, which is actually connected to the memory card interface power circuit. The transistor, the LED is on this board, but it's underneath the power wire, so not visible in this picture. On the back side of the same board, we see more of the wiring and also the memory card interface. The Arduino Pro Mini is the smallest of the Arduino family of controllers. The Arduino is a public domain open source design. It doesn't mean it's an open source to buy. It's not free. You still have to pay for them, but they're not expensive. They run typically about $7 or $8 at Amazon. You typically buy them in quantities. Usually it's like 3 for $15 or 3 for $17 or something like that. The Arduino Pro Mini has 32K of main memory, 1K of double EEPROM, and an ATmega 328 processor. It's not the most powerful thing there is, but it's powerful enough to do this project. It's enough. It's not more than enough, but it's enough. It has enough power to handle what we're doing here. The biggest thing about the Arduino Pro Mini is that it has some very useful low power modes. If you get all the power modes set up right, you can make it consume less than 500 microamps when it's asleep. That's not a lot of power. The main memory on the Arduino is a CMOS type, and so even when it's unpowered, it retains its program. That means once you put the program into it, it stays there until you put another program in it. Even if you disconnect all the power, stick it up on the shelf and let it sit for a while. The Arduino Pro Mini comes in two versions. One is an 8 MHz 3.3 volt version. The other is a 16 MHz 5 volt version. The 16 MHz version is far more common. It's pretty easy to get the two mixed up. In fact, one of the vendors that I used to buy these from would often send me 16 MHz parts even though I ordered 8 MHz parts. Be sure you order the 8 MHz 3.3 volt part. The 3.3 volt part will run at lower voltages than the 16 MHz 5 volt version. And with given our power source of 18650 batteries, that's pretty important. The photo shows a modified Arduino Pro Mini. This has two modifications on it. The first is that the LEDs have been removed off the board. There's two LEDs, one for power and one as just a generic indicator. Both of those have been removed on this board. And the other modification is adding two wires for the I2C interface coming out of connections A4 and A5. That's the blue wire, the purple wire, and the white wire. On the left of this, the pin header that's bent over at an angle is the interface to the computer that you use to program it. That's normally not connected to anything when it's just doing its thing. When it's being used as a cave intrusion detector, there will be no connections on those pins. Those pins are only there for programming it. The TSL2591 light sensor is a very sensitive device. It has a large dynamic range from about 1/1,000,000th of a lux up to about 88,000 lux. According to the datasheet, it's about 600 million to 1. That's a lot of range. It will pick up a candle at 50 feet. It's that sensitive. So a caver going by with a light, fairly bright light, even a moderately bright light, will trigger the thing pretty easily, even if it's behind a rock. It consumes about 300 microamps when it's active, and it has to be active all the time because this is the first active item in the system. Whenever anybody walks by with a light, this is the first thing that triggers. It has to be alive so that it can trigger an interrupt to the Arduino, wake up the Arduino and get the data recorded. The interface bus is I2C, and there is modification required on the new versions of the TSL2591. For some reason, they put a power LED on it, on a light sensor. I don't understand why that is, but they did, and that has to be taken off. Not only does it save power, but it allows the light sensor to be set at its highest sensitivity. These light sensors are the single most expensive component. They run about $10 a piece from Adafruit or Amazon, You can pay more. I've seen them go for up to $20 or $25. The $10 part is plenty good enough. This is the newer version, and the LED that is to be removed is in the upper left corner, right next to the socket, between the socket and the mounting hole. The DS3231 real-time clock is a temperature compensated device. It's about 2 parts per million accuracy between 0 and 40 Celsius, which is very, very usable in a cave. Where all of the caves that we deal with are between those temperatures. Besides the real-time clock, there is a temperature sensor on the clock, and its data can be read. I'm not using that in this project, but it is available. It's not terribly accurate. It's probably only good to about 1/2 degree Fahrenheit or thereabouts. The clock uses a CR2032 coin cell as its battery backup. It tracks day, month, and year in addition to time, and that includes leap years up to 2100. So basically, once you set it, you can forget it. It just keeps the right time no matter what the year is. I found these to be accurate to within about a minute in 3 months, which is not too bad. For the purpose we're using it for, that's plenty good enough. The interface to it for data and programming is I2C. So the I2C bus from the Arduino is going to run both this and the light sensor. There are 2 programmable alarms on the real-time clock, either of which can generate an interrupt. Now, there's only one interrupt line, so you have to read a data register to figure out which alarm triggered the interrupt. That's not an issue in this project because we're only using one alarm. We know that whenever the interrupt is triggered, it was our one alarm that did it. There is a modification required. There's an LED and a resistor to be removed. Those are pretty straightforward. The LED is a power indicator, and all it does is consume power. The resistor is set up to charge a rechargeable CR2032 battery. We're not using those, but even if we're not using them, it does draw some current from the power source. These things run about $2 on Amazon. This picture shows the front side and the back side of the DS3231 clock chip. The micro SD card interface. There are dozens of suitable devices. It's very generic. They're about 50 cents on Amazon. I typically buy them in quantities of 10 for about $5 or $5.50. The 2 things that you need to be sure of here is that you buy one that supports SPI, Serial Peripheral Interface, and that uses 3.3 volt logic natively. Some micro SD card interfaces are set up to use 5 volts. They have an onboard 3.3 volt regulator to knock it down to the 3.3 volts that a micro SD memory card uses. That will not be useful in our project because we're not going to feed it 5 volts. We're only going to feed it about 3.3. So we want to make sure we get one that will run natively on 3.3 volts. Most of them do. The 5 volt parts on this are not that common. The micro SD memory card does have some requirements. These are, pretty generic. You can buy them just about anywhere. But for this project, the card must be under 2 gigabytes of capacity. This is a limitation of the Arduino software. The device driver software that runs in the Arduino is memory limited. With only 32K of memory, you can't run big drivers. As such, it only knows how to handle FAT12 and FAT16 file systems. It does not know how to handle the VFAT and the exFAT file systems. It does not know how to handle long file names. It cannot handle file systems larger than 2 gigabytes. You can probably use a 4 gigabyte card as long as you format it with a partition that's under 2 gigabytes. The capacity requirement for this project is really minimal. If you were to record a light detection event every minute for a couple of years, you might use about a megabyte of data. It's really minimal, so the size is almost irrelevant. Lower capacity cards generally take less power. Look around on eBay for older stock. The cards that I like to buy when I can get them are old Verizon cards of 512 megabytes capacity. These cards have about the lowest power drain of any of the cards that I've seen. They are kind of hard to find. The last time I looked on eBay, the cards themselves were $6 or $8, but the shipping was $20 per card because they had to come out of the UK. Look around, keep an eye on eBay, look for older stock, and you can find something. This is what the memory card interface and the memory card look like. There's not a whole lot on that memory card interface. It's a pretty simple device. The PermaProto half-size board is the foundation on which all of the other components are mounted. It duplicates the layout of the breadboard, having a power rail down each side and having cross-connected pads down the middle. It provides a firm foundation to mount the components, about $2.50 a board at Amazon. I buy them in packages of 4 for $10 or $11. A custom board would be nice, but for low volume projects like this, they are expensive and take a long time to obtain. Another issue with a custom board is that once you get the layout done, you're stuck with it. The memory card interface in particular comes in a whole bunch of different versions, and the pinouts on it vary slightly from one version to another. So using the prototype board means you can change the wiring on the fly as you build each one so that it matches the memory card interface that you're using. The very first Cave Intrusion Detectors that I built on a popsicle stick using double-sided foam tape to glue the components to it. The wiring was all point-to-point, hand wiring. It was a pain in the you-know-what to build. We put that in a cave for several months. It wound up not working very well because we had a bad battery pack on it. When we pulled that out of the cave after about 6 months, the double-sided foam tape had disintegrated. It was no longer holding the components onto the popsicle stick. And there was a strong smell of hydrocarbons coming from the jar. Some of the connections and solder points on the various boards had corroded slightly. I had to take some sandpaper and sand them down in order to reuse them. They were all still usable. They were just had some corrosion on them. So building the Cave Intrusion Detector on this kind of a half-size prototype board is a much better way to do things. There are miscellaneous parts that go along with the Cave Intrusion Detector. A 2N7000 transistor is in the negative power line going to the memory card interface. The memory card interface will leak some current through the control lines to the negative ground unless you put a switch in there. So this 2N7000 transistor turns off the memory card interface. It's wired with its gate to one of the output lines on the Arduino, and this program is set up so that before any writes happen to the memory card, it turns on the device. There's an LED and a current limiting resistor to provide some operational feedback. Mainly, they are set up, the program is set up so that whenever it writes to the memory card, it turns on this LED. It gives kind of a visual feedback. It's not really necessary. You could get along without it. Coax power connectors for the battery pack. I'll talk more about the battery pack in a little bit. 22 gauge hookup wire, 0.1 microfarad ceramic disc capacitors for power line decoupling, 18650 lithium ion batteries, and a container, which I talked about right up front. The battery pack. Any DC power source between approximately 3.0 and 3.6 volts can be used. The nominal requirement is 3.3 volts. That's what everything is really designed to run on. Max voltage is around 3.8 according to the data sheets. On some of the boards, that is the max voltage allowed on them. Most of the parts will work down to around 2.8 or 2.9 volts. This range of voltage falls very comfortably within the working range of an 18650 lithium-ion battery. 18650 battery has a nominal voltage of 3.4. A fully charged battery at open circuit will be just about 4 volts, but once you put any kind of a load on it, it drops down a couple of tenths and gets under that maximum voltage. At about 3.0 volts, they are 95% 50% or more discharged. So that's pretty much the limit on their life. 18650 batteries are readily available. However, most of the batteries that you see, especially on Amazon, are cheap Chinese knockoffs. They're snake oil. In one of the other presentations I've done for this convention, I go into great detail about testing batteries and finding out what their capacity is. The 18650 battery, you can tell a good one by 2 or 3 characteristics. The first is it weighs around 45 grams. If you get an 18650 that weighs less than around 45 grams, it's bogus. It's a cheap knockoff. The second thing is looking at its rated capacity. Any 18650 that's rated for more than about 3400 milliamp hours is bogus. You cannot fit more than that number of milliamp hours into that size of a container using that chemistry. It's just physically not possible. Batteries which advertise themselves as 5000 or 10,000 milliamp hours generally have a true capacity of less than 1000 milliamp hours, 800 to 900 milliamp hours, and some of them even less than that. Getting 18650s off of Amazon is really almost impossible. You need to go to a specialty store like 18650batterystore.com. You can also use 3 AA batteries in series. The runtime is shorter, but they work very well. The system takes about 900 microamps when it's asleep. That covers all of the components that are on it. For round number figuring, call it 1 milliamp. So a battery which has a capacity of 3000 milliamp hours will run the system in theory for 3000 hours. That's about 2.5 to 3 months. So 2 batteries in parallel will run the system for about 6 months. Remember that this system spends almost all of its time asleep. It hardly ever wakes up, and when it does, it's only for about 15 seconds at a time, just long enough to pull a reading off the light sensor, write it to the memory card, and go back to sleep. The programming is done with an Arduino IDE. This is free software. It's available for Windows, Linux, and Mac OS, and you can download it from the website that's shown there. You also require an FTDI cable to download the programs from the computer to the Arduino. The FTDI cable has a USB interface connector on one end and a 6-pin connector on the other end that plugs into that angled connector on the Arduino that I described earlier. The programming language is a subset of C++. This slide shows an example of a part of the code that actually runs the Cave Intrusion Detector. Most of what's here is actually declarations, not executable code. But it gives you a flavor for what you're in for. C++ is not the easiest programming language to learn. It's quite versatile. It makes very small programs, and they run very fast because they are basically assembly or machine language code once you get done with it. When you go to build these detectors, plan on 3 to 4 hours for each completed detector. And that's after you've had some experience in doing the builds and assuming that you're pretty good at doing soldering. I have made some detailed videos on how to do the build. They're on my YouTube channel. I also have a document that gives a wiring diagram. I have a schematic diagram, and I have a bill of materials spreadsheet which shows URLs and pricing and sourcing for all of the components. I'm not sure at this point how we're going to make those available, as I'm creating this video in late June, and I don't know yet how we're going to make these available a month from now when the convention actually starts. But we'll figure out a way. Something will be done for that. This does require some skill at soldering small connections. If you're not comfortable with that, either learn it, which is not difficult, or find someone else to build the results to date. We deployed one detector in Slough Bottom Hollow Cave, a gray bat maternity cave in southern Missouri. That one is the one that I built on a popsicle stick, and as I noted, it did not survive very well. We used the wrong kind of batteries. That was before we fully understood all of the issues around 18650 batteries. It lasted, we figure, about a month. It detected no events during that time, which was probably correct. There probably was no intrusions during that time. The latest design is currently deployed in 2 caves. We won't have any results from them until after the convention is over with. We won't have a chance to visit those caves and pick them up until mid to late August. So we don't know what they are showing right now. There is considerable interest among various government agencies: Bureau of Land Management, Fish and Wildlife Service, National Park Service, Missouri Department of Conservation. We haven't come to any kind of arrangements on it yet. I don't want to be in the business of manufacturing these things, so we're not quite sure. Well, we just don't know what's going to happen. But they are certainly interested, and we think in 6 months or a year we'll probably have something worked out and be getting more of these into a cave. In future development, well, obviously we want to put more of them in caves and see what kind of data we can collect. I do plan at least one fairly important change to the program. I want to set it up so that once a week, or at some regular interval anyway, the system wakes itself up, writes a time and date stamp to its data file, and goes back to sleep, regardless of whether there was a light detection event or not. That will be useful in letting us know just how long they actually do run on a set of batteries. The other development is fairly recent. Raspberry Pi recently issued a new device called the Pico, which is a microcontroller. I have obtained a couple of Picos, and I want to test them with this system to see how they're going to work. I suspect they will not be as good as the Arduino for this, and mostly that's because the power consumption on the Pico is quite a bit higher than it is on the Arduino Pro Mini. Even when it's asleep, the datasheet for the Pico says that its power consumption is in the range of 2 milliamps. That's over 4 times as much as the as the Arduino consumes. And it probably is not possible to get it any lower than that. The plus side to the Raspberry Pi Pico, first, is that it can be programmed in Python, a much easier programming language. And second, it has far more memory capacity and far more processor capacity than the Arduino. The Arduino is adequate, but not any more than that. The Raspberry Pi Pico would be far more than adequate in terms of processing power and memory for doing this job. So that's the end of my presentation. Thank you for attending. I hope you learned something. I hope it gets you interested in looking at projects using Arduinos and other kinds of microcontrollers in a cave.